In this module, we continue to discuss basic probability and statistics in the context of manufacturing measurement applications. The key concept is that data from repeated measurements usually vary. Distributions of that variation can be modeled and used to estimate the probability of measurements and our confidence that measurements will occur over a specific range.
This video shows a prototype prosthetic limb during a variety of locomotive tests, walking on level ground, up slopes, up and down stairs, sit to stand, squatting, and even simple extension and flexion movements. This motorized prosthetic leg, shown in the diagram on the left, is controlled by surface EMG sensors on upper leg muscles, which in effect move the knee naturally just by thinking. It is tested both with people who have a transfemoral amputation and with people who have intact legs. This latter robo-crutch mode uses a cast-like adapter and appears to have promise as an assistive crutch, but it has a problem that could prevent its success. Can you guess what the issue is? We'll use this as a motivational case study for our introduction to manufacturing measurement statistics. Let's imagine we're a medical device company that seeks to manufacture this robo-crutch, potentially for lower extremity rehabilitation. As we can see in the video, the prototype device was initially researched by engineering students as an actively controlled prosthetic limb. The design drawing is shown on the right. The device contains a novel EMG-controlled knee joint with a compact ball screw, shown at the top right, and a DC motor. It's capable of power-requisite tasks such as walking up slopes, standing up, squatting, and even walking upstairs. Now, preliminary tests of the product were successful. However, as you probably could hear in the video, customer surveys indicated that the device is simply too loud for practical use. If a manufacturing engineer can reduce ball screw bearing noise during the assembly process, we may be able to take the product to production. So an obvious place to investigate noise is in the ball bearings. Many small bearings are tightly packed around the ball screw within a ball nut assembly. Unusually high variation in ball bearing geometry could be a big source of noise. Consider inspecting a large vendor-supplied box containing thousands of similarly sized small round bearings. We might seek to better understand the size of the bearings and, more importantly, the variation in size. But it's not practical to measure all of the bearings, so we might measure 24 from the thousands in the box. This selection of diameter measurements forms a data set, which we use to infer information about the entire box of bearings, such as the average diameter and its variation. The population is, of course, all possible values of a measured variable. Sometimes a population is countable, knowable, or even known. But often the actual population is not practically known or knowable. Imagine measuring the size of all of the fish in a lake. The only way to measure the population may be to drain the lake, and that's definitely not a good idea. In the case of a box of bearings packed by weight, the manufacturer might not even know the exact number of bearings in the box. Sampling is the process of obtaining data through repeated measurements of a variable, preferably under fixed operating conditions. Drawing a dozen bearings from the box is, of course, sampling. But imagine if smaller bearings settle in a box like this. We must be careful to ensure that the sampling process selects representative samples from the population without bias. In statistics, the sample is simply the subset of values taken from a population. The measurand is the variable being measured. In this case, the ball diameter is the measurand. We make measurements that we use to infer things about the measured variable. In this case, we sampled bearings and measured bearing diameter. But what questions are we trying to answer? The core question is how close are the measurements taken from the small data set at estimating the actual size and variation of all of the bearings? Also, if we selected a different set of 24 bearings, would we expect the values to be the same? What is the average or mean value based on this finite sample? And how well does the mean represent the entire population? More importantly, do the variations found ensure we can meet tolerances for the population as a whole? And how good are these results? These questions have their answers in probability and statistics. These questions imply that we should have clear goals for this type of analysis. Of course, we want to reduce noise in the ball screw, but when it comes to our analysis of sample bearings, we more generally want to be able to quantify 1. A single representative value that best characterizes the average of the measured data, the average diameter of the 24 sampled. 2. A representative value that provides a measure of the variation in the measured data set, perhaps the standard deviation or the range of diameters. And 3. How well the average of the data set represents the true average of the entire population of the measured variable. The value of the single best representative value in one can vary with repeated data sets, so the difference between it and the true average value of the population is a type of random error. Our third goal requires establishing an interval within which the true value of the population is expected to lie. This interval quantifies the probable range of this random error, and it's called the random uncertainty. To achieve those goals and better understand error and uncertainty, we need to look more closely at an individual measurement. It's helpful in statistical measurement applications to introduce the notion of a true value, the exact value of a variable, distinct from the measured value indicated by the measurement system. While it is possible that the measured value is the true value, practical limitations often introduce errors. Errors are the difference between the measured and true values. Error sources are diverse. Just to name a few, errors can be rooted in instrument accuracy, calibration, human error, data acquisition, process variation, changes over time or temperature, or just natural variation. Even the most accurate measurement instruments with the smallest of resolutions have some real-world limits to their accuracy. And physically, a part, like a bearing, does in fact have some true value. In manufacturing statistics, often simple counting operations like output, yield, or backlog might not have any error for reliable systems. But measurements of physical or process variables, also known as random variables like size, pressure, temperature, force, flow rates or speeds, or even key operating variables like time and cost, are likely to be subject to the effects of random variation. Often, an estimate for the magnitude of error is based on a reference value. The reference value can be the standard from an instrument's calibration, or the range, or the maximum value. This percent accuracy, or relative accuracy, relative error, or just known as accuracy, is helpful at evaluating a measurement. Accuracy generally refers to the closeness of agreement between the measured value and the true value, often as a percentage. Notice that the absolute value of error is used because magnitude of error is the primary concern. Errors cause a measured value to differ from its true value. We see this when we take repeated measurements of a variable and don't get the same results. Repetitions can be handled differently depending on what we're trying to learn. In our scenario, we independently sample 24 bearings from a box and repeat the measurement of each diameter. Our aim was to understand variation in the entire box. We could also imagine measuring a single bearing repeatedly, but say at different orientations around its perimeter, to understand its roundedness. Or we could measure the same bearing at different times of day or different temperatures. We could even use different people or instruments to repeat a measurement. But no matter the repetition method, if we observe different values of a measurement, we classify these differences as errors. We conventionally classify these errors into two main categories: systematic errors and random errors. If we plot measured values by measurement reading number, we can see that systematic errors generally result in an offset from the true or known value, while random errors scatter around the apparent measured average value. In our ball bearing measurements, an offset could be caused by a micrometer calibration error, or even just oil or gunk on the micrometer head. Natural variation in a measurement without a known or controllable cause is generally considered random error. If there is a systematic cause of variation, it generally presents as an offset that can be corrected. Because of this, we initially assume that systematic errors are negligible. So the average error is 0, and we assume that the best estimate of the true value is the mean value. Dart throwing is a surprisingly useful illustration for error and accuracy concepts. The best case scenario in terms of accuracy and precision is when all of the darts hit the bullseye, as evidenced in the middle. If, however, darts consistently hit the same spot just left of the target, as shown on the leftmost board, the thrower is precise and has high repeatability or low random error, but a systematic error is obvious. A good thrower might be able to correct the aim and fix the systematic offset. When dart throws vary around the target as shown on the right, random error is higher. Accuracy and precision are low. This illustration is even more helpful if we consider a scenario on the right without a known target. Imagine the target turned over on the back of a wall. In this case, even with consistent throws, there is no absolute reference for performance. We don't really know where the true target is. You don't know what you don't know, in other words. But we can use statistical methods to estimate and analyze errors and measurement accuracy. Now, as a fun dart throwing aside, check out Mark Rober's video about a dartboard that corrects errors in every throw for a perfect bullseye. The big challenge with these measurement error concepts is that both the true value of a variable and the actual measurement errors are rarely known exactly. But based on available information, an operator may feel confident that the error is within certain bounds, a plus or minus range of the reading. This range estimate is the uncertainty. Uncertainty is a property of a test result. Uncertainty values are error estimates assigned to an instrument or a measurement. Formally, our goal is to estimate the true value of a variable x prime using the average observed value x bar and uncertainty estimate range u, calculated with some probability p. Uncertainty analysis approximates errors using standard methodologies. Generally, we combine uncertainty of estimates of random and systematic errors, but here we mainly focus on how to estimate the uncertainty arising from the effect of random error or random uncertainty. As we previously discussed, a sampling of the variable under fixed or controlled conditions renders a sample, which is a finite set of data points. Intuitively, we expect that if the number of sample points is very small, the estimate of the true value, x prime, could be influenced significantly by any one data point. With a larger data sample, the relative influence of any one point becomes smaller. As the number of points increases toward the population size, all variations of the measurements are included in the sample data set. The more samples we take, the smaller our uncertainty becomes. But how does that influence the uncertainty range and probability? We need to better understand how data is distributed to confidently state uncertainty. That concludes our introduction to manufacturing measurement statistics concepts. At this point, we've established some key questions, goals, and terms such as error, uncertainty, and accuracy. In the next module, we'll look more closely at distributions and discuss manufacturing measurement applications of probability and statistics.